Welcome to Night Rhythm. Tonight we are examining what happens when the brain is forced to operate without sleep. Not vaguely, but hour by hour. What changes after 24 hours awake? Why does decision-making degrade at 48 hours? And what begins to occur neurologically after 72 hours without rest? This episode walks through the measurable effects of sleep deprivation on attention, emotion, metabolism, and neural communication. More importantly, we will examine practical steps that protect cognitive stability when sleep loss is unavoidable. Sleep is not optional maintenance. It is neurological infrastructure. Let's examine what happens when that infrastructure is temporarily removed. Sleep deprivation begins influencing the brain long before a person feels extreme exhaustion. After roughly 16 hours awake, adenosine, the molecule that tracks cellular energy use, has accumulated substantially in the brain. Adenosine binds two receptors that slow neural firing and increase the sensation of sleep pressure. This biochemical signal is the brain's way of requesting shutdown for repair and metabolic recalibration. When wakefulness extends beyond the natural circadian window, the prefrontal cortex becomes the first region to lose efficiency. This area governs planning, impulse control, and judgment. Functional imaging studies show reduced metabolic activity here after prolonged wakefulness. As a result, reaction time slows, risk assessment becomes inconsistent, and simple decisions begin requiring more mental effort. At approximately 24 hours awake, cognitive performance resembles the impairment associated with moderate alcohol intoxication. Laboratory measurements show measurable reductions in attention stability and short-term memory accuracy. The brain begins compensating by recruiting additional neural networks, essentially overworking secondary systems to maintain baseline functioning. One early symptom people often notice is microsleep. These are involuntary lapses in consciousness lasting a few seconds. During microsleep events, portions of the brain temporarily shut down, despite the person appearing awake. Drivers and machine operators are particularly vulnerable because microsleep can occur without warning, and without immediate awareness afterward. Emotion regulation also deteriorates after the first full day without sleep. The amygdala, a region involved in emotional processing, becomes significantly more reactive. Meanwhile, the prefrontal cortex, which normally moderates emotional responses, remains suppressed. The result is exaggerated emotional reactions, irritability, and reduced tolerance for stress or frustration. Metabolic processes begin shifting as well. Sleep deprivation increases cortisol, the body's primary stress hormone. Elevated cortisol maintains wakefulness temporarily, but disrupts glucose regulation. Over time, this hormonal imbalance contributes to increased appetite and reduced insulin sensitivity, even during short periods of sleep restriction. At 36 to 48 hours awake, communication between neurons becomes less synchronized. Brain imaging shows weakened connectivity between regions responsible for attention and working memory. The brain is still operating, but coordination between systems begins degrading, much like a computer running too many programs without restarting. Visual perception also becomes less reliable during extended wakefulness. Small distortions in depth perception, contrast, sensitivity, and motion tracking may appear. These changes occur because the visual cortex depends heavily on REM sleep for calibration. Without that recalibration, sensory interpretation gradually becomes less precise. Memory formation becomes particularly fragile after 2 nights without sleep. The hippocampus, which transfers short-term experiences into long-term storage, relies on slow-wave sleep cycles to stabilize new information. When those cycles are skipped, memories remain incomplete or fragmented, explaining why severely tired individuals struggle to retain new details. Attention stability becomes the next major vulnerability. In laboratory vigilance tests, individuals deprived of sleep show sharply increased lapses in attention lasting several seconds. These gaps occur even when participants are attempting to focus. The brain's alertness network simply cannot maintain consistent activation. Around 48 hours awake, some individuals begin experiencing mild perceptual disturbances. These may include brief visual misinterpretations or exaggerated sensitivity to light and sound. These effects occur because the thalamus, the brain's sensory relay station, becomes less efficient at filtering incoming signals during prolonged wakefulness. Despite these changes, the brain continues attempting to preserve core survival functions. Basic motor control and language remain relatively stable longer than executive functions. This explains why someone can still hold a conversation while simultaneously making poor decisions or forgetting basic instructions. By 60 hours awake, mental fatigue becomes physically visible. Reaction times slow dramatically. Eye tracking becomes irregular, and blinking frequency increases. These physical markers reflect rising sleep pressure combined with circadian signals demanding restorative sleep. At roughly 72 hours awake, severe cognitive instability can develop. Concentration becomes fragmented, and individuals may experience short episodes of confusion or disorientation. These symptoms are the brain's final warning that restorative sleep is urgently required. Fortunately, recovery from short-term sleep deprivation is usually achievable. The brain prioritizes slow-wave sleep during the next sleep opportunity, allowing deeper restoration early in the night. This process helps repair metabolic waste accumulation and rebalance neurotransmitter systems. If you must remain awake longer than usual, such as during travel, emergency work, or caregiving, protect cognitive stability through structured strategies. Maintain hydration, expose yourself to moderate daylight, and take short controlled breaks away from mentally demanding tasks. Strategic 20-minute naps can also restore partial alertness without entering deep sleep inertia. These short naps allow the brain to briefly reduce adenosine pressure while avoiding grogginess that follows longer daytime sleep periods. Caffeine can temporarily block adenosine receptors, delaying the sensation of fatigue. However, use it carefully. Small doses spaced several hours apart are more stable than large single doses. Excess caffeine may increase anxiety and make recovery sleep more difficult later. Most importantly, rebuild normal sleep rhythm deliberately. After sleep deprivation, aim for consistent bedtime, reduced evening light exposure, and a quiet sleep environment. Stability helps the circadian system regain alignment faster than irregular recovery sleep. Thank you for spending this time with Night Rhythm. Sleep deprivation demonstrates how precisely the brain depends on structured cycles of restoration. When sleep disappears, cognition, emotion, and perception begin shifting within hours. Protecting sleep is not indulgence, it is neurological maintenance. Guard your rhythm carefully and allow the brain the recovery it is designed to perform. If you occasionally experience sleep loss, remember that the brain is resilient when recovery is prioritized quickly. A single disrupted night does not permanently damage cognitive systems. What matters most is returning to consistent sleep timing and minimizing repeated deprivation across multiple days. Tonight, consider observing your own rhythm. Notice when mental clarity begins to fade and how strongly your body signals the need for rest. These signals are not weakness. They are biological guidance systems designed to keep the brain functioning safely and efficiently.